mechanical rotational system. So far, we have seen mechanical translational system. Mechanical translational system. Now, rotational system. Translation, linear displacement, x. Rotational system means theta. It rotates. The displacement is theta. Mechanical rotational system. Here, the application is not force, torque. The application is the input energy is torque, not force. Input energy is torque. The applied energy is torque. The displacement in the spring is theta. The displacement in the spring is theta. One end is fixed. Because of the torque, the applied torque, the displacement in the spring is theta. Therefore, the reactional force is k theta. Reactional force is k theta. Applied energy is, the reactional torque is, not reaction force, sorry. The reactional torque is k theta. Applied torque is T. Therefore, these two must be equal by Newton's law. Therefore, T equal to k theta. That is the mathematical model. Here, mass equal to 0, dashpot, no dashpot effect. Mass is 0. Therefore, the mathematical model equal to k theta. T equal to k theta. That's all. If both ends are free, then that is T equal to k multiplied by theta 1 minus theta 2. Both ends are free. This displaced by an angle theta 1. This is followed, but by theta 2 only. Therefore, net displacement in the spring, rotational displacement is net angle. This angular displacement is theta 1 minus theta 2. Therefore, T equal to k multiplied by theta 1 minus theta 2. This is rotational system. In the same way, dashpot effect. The angle is theta. Angular displacement is theta. Angular displacement is theta. The applied torque is T. Applied torque is T. Dashpot constant is B. Therefore, applied torque must be equal to TB. That is equal to B d theta by dt. That's all. B d theta by dt. But d theta by dt is angular velocity omega. That's why we can write B omega also. B omega also. If both ends are free, one end has a displacement of theta 1, other end has a displacement of theta 2. The dashpot constant is B. Therefore, B d theta 1 by dt minus d theta 2 by dt. Why theta 1 is taken as positive? Because theta 1 is in the end in which torque is applied. The end in which torque is applied. The other end has to be taken as negative. The applied torque side must be taken as positive. Therefore, theta 1 minus theta 2. If it is both ends are free, the mathematical model is torque equal to B d theta 1 by dt minus d theta 2 by dt, or B multiplied by omega 1 minus omega 2. That's all. One more that is missing. That is, it has an inertia. It has an inertia J. Applied torque is T. Displacement is theta. Displacement is theta. There, mass M. Here, moment of inertia J. Moment of inertia J is a constant. Because of mass only, it is constant. Therefore, it doesn't have any spring effect. It doesn't have any dashpot effect. In that case, the applied torque is as a reactional torque of J d square theta by dt square. D square theta by dt square, or J, if you know the velocity, d omega by dt, or J angular acceleration, alpha. The R you can write J alpha. If both ends are free, that inertia, both ends are free. This end we applied a torque T. This end has a displacement of theta 1. This end has a displacement of theta 2. In that case, the mathematical model is T equal to J d square theta 1 by dt square minus d square theta 2 by dt square. Or this can also be written as J d omega 1 by dt minus d omega 2 by dt. Or which can also be written as J alpha 1 minus alpha 2. That's all. This is for rotational system. What are the constants and variables in that rotational system? Torque, the applied energy, is in the form of torque. Its unit is Newton meter. Torque is what? Suppose this is subjected to a torque of T, means the force is applied at this point. Linear force F is applied here. This is the distance X. Therefore, T equal to the torque equal to Fx. That's why the unit is Newton meter. Angular displacement is theta radians. Angular displacement is theta radians. Angular velocity is omega t radians per second. Angular acceleration is radians per second square. Linear means here what we will say meter. Linear means here meter per second. Linear means meter per second square acceleration. Here radians per second square. The moment of inertia J, the unit is kg meter square. Kg meter square. The stiffness constant of the spring K is Newton meter per second per radian. Newton meter per radian. And the damping torque is, that is B, is Newton meter per radian per second. Per radian per second. That's all. So these are we should know the units as well as the variables and the constants used in the rotational system that we have seen. Here also we have to draw the free body diagram. What are the applied torques we should mention? What are the reaction torques we have to mention? Then by using law of motion, we have to write the equation. Here one end is fixed. Therefore, T equal to the applied torque equal to the reactional torque equal to J d square theta by dt square. J d square theta by dt square. If it is a dash part, one end is fixed. In that case, B d theta by dt. Or B omega. J d omega by dt for mass one end fixed. The diagram is wrong. Huh? If it is spring, it is k theta. If you know the velocity, angular velocity, if you know, that is k integral of omega dt. If both ends are free, means in the case of dashpot, omega 1, b omega 1 minus omega 2, or b d theta 1 minus d theta 2 by dt. In the case of spring with both ends are free, means k theta 1 minus theta 2. If you know the velocity, integral of omega 1 minus omega 2. That's all. So these are all we should remember to obtain the mathematical model. Rotational system, we have to obtain the mathematical model. This is the given rotational system. This is the given rotational system. The applied torque is, this is some problem in rotational system. So this is the torque applied. One end is fixed. One end is fixed. Torque applied is T. The displacement, one end only. Other end is fixed. That is theta. The spring constant is K. The spring constant is K. Dashpot constant is B. The moment of inertia is J. This should be here. We can write the mathematical model. If you draw the free body diagram, J, the applied torque is T. Because of that, that end has a displacement of theta. The reactional torques are Tk, Tb, Tj. Tk is equal to what? K theta. Tb equal to V d theta by dt. Tj equal to J d square theta by dt square. So if you substitute these values, we'll get T equal to J d square theta by dt square plus B d theta by dt plus K theta. This is the mathematical model in time domain. To obtain mathematical model in frequency domain, we have to take Laplace transform. Laplace transform of this variable. T is variable. Applied torque is variable. T of S. That's all. We do not know the form of input. Torque. That's all. So we have to write T of S. If you write Laplace transform of this J d square theta by dt square, assuming zero initial condition, J s square theta of S. B d theta by theta. If you write the Laplace transform, assuming zero initial condition, B s d theta of S. K theta, if you write K theta of S. Theta is the output. Displacement is the output. Displacement is the output. So we have to find theta of S upon the input T of S. So take theta S outside, what you will get? Theta of S outside, if you take Js square plus Bs plus K. Therefore, theta of S upon T of S, the transfer function is output. Laplace transform of output by Laplace transform of input is 1 upon Js square plus Bs plus K. Js square plus Bs plus K. This is second order differential equation. Second order differential equation.